This is for our chapter 1.3 class, Thinking Like a Scientist. Here are the objectives for this lecture. First off, be able to define observation. Well, an observation is anything you notice about the physical world around you. So let's say that you wake up in the morning and it is dark. That's an observation. If you wake up in the morning and it is light, that's also an observation. You start making observations from literally the moment you wake up. What is a hypothesis? A hypothesis is something you will say that explains your observation. So it's an explanation that can be disproven. If you wake up in the morning and it is dark, you might make the hypothesis it is dark because it's still night out. So it's morning, but it's like 2 in the morning. That's a hypothesis. It can be disproven if, say, you look at the clock and it says 8 a.m. and you think, why is it dark then? Well, you're going to have to make another hypothesis. And looking at the clock, that was an experiment. An experiment is something you can do to support or disprove your hypothesis. So look out, it's dark. That's an observation. It must be 2 in the morning. Hypothesis, I'm going to check that by checking the clock. Experiment. It gets disproven or it gets supported. We're going to look at independent variable, dependent variable, model, theory, and scientific law later in this lecture, so definitely keep your pens handy for defining those. Be able to list, in order, the steps of the scientific process. So a question I may ask you on the exam is, put these following things in order, or which comes third. Be able to differentiate between laws and theories, and this will be throughout the course. So, for example, atomic theory is just a theory. The law of universal gravitation is a law that we're going to cover in physics. And last, use skills of analysis and interpretation in a scientific context. That one seems a bit vaguer, and it's got that MSPS 1-1. That's because that is a objective that was placed here for the overall what are we learning in this course and how does it relate to your high school education. So here's an experiment that was done to explain the idea of phlogiston. You've probably not heard of phlogiston because it was a disproven hypothesis. The hypothesis was that flammable things contained an element known as phlogiston, and they lost it to the air when they burned. So the phlogiston went away, and now you have a phlogiston-free compound. Lavoisier was a scientist that tested this hypothesis. What he did is he weighed the air and he weighed some metals before burning them. So he burned, say, a strip of magnesium, and he would find that the magnesium was actually heavier than it was at the start, but that the air had lost mass. So the hypothesis for why this was true was that the metal is actually taking up something from the air when it burns. And this is true. What happens is magnesium will react with oxygen to make magnesium oxide. So the ashes that come out of magnesium burning are going to actually weigh more than the magnesium that was started with. The scientific method is what we use to make observations, hypothesize, make a prediction, run an experiment, and look at the results. So you'll notice that there's this kind of prediction here that we put in between hypothesis and experiment. The prediction is a very specific statement. So we generally make this as an if-then statement. So it's very easy to prove or disprove. A hypothesis is generally actually a little more vague, but we're generally going to look at hypotheses in terms of being able to make a prediction using the hypothesis. So the hypothesis that phlogiston exists. The prediction would be if we burn something, then it will weigh less. And the experiment being actually burning some magnesium, the results being these magnesium ashes are heavier than the magnesium was to start with. And the air has lost some mass. The oxygen has gone into the ashes. This is how the scientific method was used to disprove the phlogiston hypothesis. Now, we're going to talk in class about different experiments. We're going to talk about independent and dependent variables. The independent variable can also be known as the manipulated variable. It's what we are changing. So let's say that I come up with the hypothesis that iron supplements increase your ability to lift things in the gym. Okay, That's easily tested. So that hypothesis can be tested. We'll make the prediction that if I give some individuals iron supplements, then they will lift more in the gym. They get mad shredded and stuff. So what we do is we get two groups. One group is going to have the iron supplements. One group is not going to have these supplements. And they vary. These two groups vary. How do they vary? By the independent variable. The variable is not dependent on anything. It's just my choice to give some people iron and some people not. The dependent variable will depend on the independent variable. The dependent variable is also known as the responding variable. And the dependent variable in this case is how much the individual can lift. So if the individuals who get the iron supplements are now pumping mad iron in the gym, then we would say that, well, your hypothesis has been supported by the experiment of giving people iron and seeing if they lift more. So your results show that the dependent variable is depending on the independent variable in the way that you expected. So you can think of some other experiments. Anytime you're giving individuals drugs to see if they have an improvement in their disease, the giving of a certain drug is your independent variable. In lab, we will be doing the bubble lab, and the independent variable in that is going to be whether we add table sugar or table salt or nothing to our dish detergent. That's going to be your independent variable. The dependent variable is how many bubbles we can blow. Now, not everything can be tested in a chemistry lab. For example, the idea of the Big Bang cannot be tested in a chemistry lab, so we use something called a model. A model is some sort of representation for something that we can't do in a lab. So most climate models are going to hypothesize that if your ocean was this warm, then we would have this many hurricanes. Okay, that can be tested. How? By a model. Obviously, we can't go out there, stick thermometers all over the ocean and see how hot it gets and then go, okay, now we'll test. We're going to warm up the oceans until it gets warm enough, then we'll see how many hurricanes. No, that's a terrible idea. Most fish would disapprove. And also it would cost a lot of money. So models are things we use when we can't do it in the lab. Theories are going to be well-tested explanations when you have many observations and many hypotheses. For example, we note that as oceans get warmer, they make more hurricanes. That's why we have hurricanes in summer and not in winter. So the temperature of the ocean is going to have an effect on the number of hurricanes that happens. That's our theory. It's been pretty well shown by many observations and hypotheses. A scientific law is a statement that summarizes many observations or experiments. Many scientific laws are strictly mathematical. So these are going to be things like gas law. How do gases behave at a standard temperature and pressure? Turns out they're very, very predictable, and those are going to be your gas laws. Scientists need to share their findings. We do not exist in a void, and we're going to see that peer-reviewed publications and presentations at conferences are two ways that scientists are going to communicate to one another. Scientists also collaborate with one another. When I was a biologist, it would help me to discuss things with other biologists and even with some chemists. So I might go talk to a physicist if I have a certain question about how a molecule will interact that would be more on the physics side than on the chemistry side. None of us can be experts in everything, so we all need to stop, collaborate, and listen. So I want you to think about some problems scientists are working to solve and notice that there are many scientists probably working together, collaborating on these problems.